Hi, this is Dr. Rajeshwar from Pharma Tube. In the previous lesson, we learnt the Aldol condensation of aldehydes and ketones. Hit the I button on top right of this video to watch it. For the other topics of organic chemistry, links are given in the description below this video. Watch them. In this video, we shall learn the crossed Aldol condensation of aldehydes and ketones. The preceding video considered only aldol reactions between two molecules of same aldehyde or ketone. When two different carbonyl compounds are used, the reaction is called a crossed aldol reaction. In other words, an aldol condensation between two different carbonyl compounds is called a crossed aldol condensation. It is sometimes known as mixed aldol condensation. When two different aldehydes, both having alpha hydrogen atoms, are combined in an aldol reaction, four different beta hydroxycarbonyl compounds are formed. Four products form because both aldehydes can lose an acidic alpha hydrogen atom and form an enolate in the presence of base. For example, the condensation between acetaldehyde, that is ethanol, and propanol. Either of ethanol and propanol reagents can form an enolate ion. Attack by the enolate of ethanol on propanol gives a product different from the one formed by attack of the enolate of propanol on ethanol. Also, self-condensations of ethanol and propanol continue to take place. Depending on the reaction conditions, various proportions of the four possible products result. In many cases, the result of a crossed aldol reaction is a difficult to separate mixture. A crossed aldol condensation can be effective if it is planned so that only one of the reactants can form an enolate ion and so that the other compound is more likely to react with the enolate. If only one of the reactants has an alpha hydrogen, only one enolate will be present in the solution. If the other reactant is present in excess or contains a particularly electrophilic carbonyl group, it is more likely to be attacked by the enolate ion. The given two reactions are successful crossed aldol condensations. The aldol products may or may not undergo dehydration depending on the reaction conditions and the structures of the products. To carry out these reactions, slowly add the compound with alpha protons to a basic solution of the compound with no alpha protons. This way, the enolate ion is formed in the presence of a large excess of the other component and the desired reaction is favored. We shall therefore consider crossed aldol condensations by two general approaches that allow control over the distribution of the products. The first approach hinges on structural factors of the carbonyl reactants and the role that favorable or unfavorable aldol addition equilibria play in determining the product distribution. In this approach, relatively weak bases such as hydroxide or an alkoxide are used in a protic solvent such as water or an alcohol. The second approach, called a directed aldol reaction, involves the use of a strong base such as lithium isopropylamide, abbreviated LDA, in an aprotic solvent. With a strong base, one reactant can be converted essentially completely to its enolate, which can then be allowed to react with the other carbonyl reactant. Crossed aldol condensations using weak bases. Crossed aldol condensations are possible with weak bases such as hydroxide or an alkoxide when one carbonyl reactant does not have an alpha hydrogen. A reactant without alpha hydrogens cannot self-condense because it cannot form an enolate. We avoid self-condensation of the other reactant, that which has an alpha hydrogen, by adding it slowly to a solution of the first reactant and the base. Under these conditions, the concentration of the reactant with an alpha hydrogen is always low and it is present mostly in its enolate form. The main reaction that takes place in between this enolate and the carbonyl compound that has no alpha hydrogens. The reactions shown here illustrate results from this approach. The crossed aldol examples shown here involve aldehydes as both reactants. A ketone can be used as one reactant because ketones do not self-condense appreciably due to steric hindrance in the aldol addition stage. Crossed aldol condensations using strong bases. One of the most effective and versatile ways to bring about a crossed aldol reaction is to use a lithium enolate obtained from a ketone as one component and an aldehyde or ketone as the other. An example of this approach, called a directed aldol reaction, is shown by the mechanism given here. In the first step, the ketone is added to LDA, which is a strong base which removes an alpha hydrogen from the ketone to produce an enolate. In the second step, the aldehyde is added and the enolate reacts with the aldehyde at its carbonyl carbon. The third step is an acid-base reaction occurs when water is added at the end, protonating the lithium alkoxide. Regioselectivity can be achieved when unsymmetrical ketones are used in directed aldol reactions by generating the kinetic enolate using lithium diisopropylamide. This ensures production of the enolate in which the proton has been removed from the less substituted alpha carbon. For example, an aldol reaction via the kinetic enolate using LDA results a single crossed aldol product. See the reaction. If this aldol reaction had been carried out in the classic way using hydroxide ion as the base, then at least two products would have been formed in significant amounts. The reaction shown here is an example of an aldol reaction that produces a mixture via both kinetic and thermodynamic enolates using a weaker base under protic conditions. This is the list of references followed for the lesson. That's all in this video, the crossed aldol condensation of aldehydes and ketones. In the next lesson, we will learn the Cannizzaro reaction. Till then, never stop learning and never stop watching my videos. Thank you for watching this video.